So my name is Nathaniel Phillips, and I'm from the Department of Economic Psychology at the University of Basel. And there, one of the main questions that we ask in our research is, how can people make good decisions based on limited, noisy information? So what are some examples of this? So consider a hiker searching for mushrooms. Now, of course, they have to avoid mushrooms that are poisonous and only take the ones that are safe. Well, how can they do this? Another one would be a soldier at a military checkpoint. Now, these soldiers at these military checkpoints, they of course need to worry about terrorists coming to attack the station. So if an oncoming car is coming towards the checkpoint, they need to quickly decide, is this a true threat or not? And finally, consider an emergency room doctor deciding how to treat a patient that's coming in complaining of some illness. And one example of this is treating patients that come to the ER complaining of chest pain. Now, the question that they need to decide is this patient truly having a heart attack or not? Now, if the patient is having a heart attack, then we want to send these patients to the coronary care bed. Now, these beds are expensive, they require a long stay, and they use a lot of space. But if the patient is not having a heart attack, then they should be sent to a regular bed. This is a much cheaper bed, it's a shorter stay, and it's a smaller space. So how can they make a good decision? Well, how do doctors typically do this? They usually use clinical judgment. So each individual physician is going to make a judgment based on their own personal experience. And this doesn't always work out so well. So in one Michigan hospital, doctors sent about 90% of patients complaining of chest pain to the ICU, although only 25% of these were actually having a heart attack. And you can imagine reasons why they're doing this. For one reason, it could be defensive medicine. So doctors could be very afraid that they don't want to have a miss. They don't want to miss out on someone that's actually having a heart attack. But the problem is if you're sending all of these false alarms to the ICU, then you're taking up valuable beds for patients that are actually having heart attacks. So what's one solution to this? One solution that's been used is a fast and frugal decision tree. And a fast and frugal decision tree, this specific one is developed by Green and Mayer, and here's how it works. So one starts by looking at ST segment changes. If there are changes to this, immediately send them to the coronary care unit. Don't consider any additional information. If not, then ask, is the chief complaint of this patient chest pain? If it's not, then they immediately go to a regular bed. And finally, we ask if any one of the following factors, and there's about 5 factors here, are true. If so, immediately send them to the coronary care unit, otherwise send them to a regular bed. And this tree was quite successful, despite the doctor's concerns about it. And in fact, this tree cut the false alarm rate in half. And this tree is still being used at the hospital. And unlike other types of algorithms that have been proposed to doctors, such as regression, this is something completely transparent that they can understand and potentially work with the algorithm developer to change. With regression, ask a doctor to do a regression analysis or to trust the results of a regression analysis, you're going to have a really hard time. So what is a fast and frugal decision tree? Well, it's simply a decision tree, but that is very, very highly restricted. And the definition is that FFT is a decision tree with exactly 2 branches from each node, where one or both of the branches must be an exit branch. And now that's in contrast to what I would call a standard decision tree, which doesn't have these requirements. So why should we use fast and frugal decision trees? Or first, actually, let me give you some examples of FFTs that have been used in the literature. So they've been used to describe how people make judgments about inferences. So for example, if I ask you if I ask an American, which city is bigger, Berlin or Dortmund, they would use a fast and frugal tree to make this decision. How do judges make bailing decisions? Well, research by Dami in 2003 found that judges actually are using fast and frugal trees. And there's other examples. For example, detecting depression, or this tree up here is used to determine whether or not banks are at a high risk of failure. So why should we be using these really simple trees? Well, for one reason, it goes back to the general claim back from Occam's razor that no more entities should be presumed to exist than are absolutely necessary. We want to keep things simple. Why should we keep them simple? Well, it helps us to focus on what's important and ignore things that maybe are not so important. So, what I'm presenting to you today is a package I wrote called FFTrees. And this is a package that is designed to create fast and frugal decision trees and display them in a way that's informative. So let me give you an example. This is a heart disease data set. So it has about 300 patients, each described by different cues from the age, sex, other demographics, also a series of medical tests. And the goal of this tree is to predict their final diagnosis, which 0 means that they do not have heart disease, and 1 indicates that they do. So how would I create trees using the function? Well, it's quite simple. First, you can install and load the package from CRAN. And then to create the trees, we just use a standard formula indicating what we're predicting. You can indicate the training data. You can also separately define the test data. And then you can add some additional tags like description of the data set and the labels for the different decisions. And these get passed to other functions. When you print an FFTrees object, you see some basic information about the trees. So for example, here, when I print out heart FFT, which is my FFTrees object, I see that there's 7 trees in here predicting diagnosis. And I'm also given some information about the one tree that maximizes a performance criterion. So in this case, this tree uses 3 Qs, TAL, CP, and CA. You get additional summary statistics about the tree in both training and test data set, and then outputs on different algorithm parameters specified. So once you've printed an object, you see how well it works. You might want to know, okay, well, what is in the tree? Well, you can do that just by running this inwords function. If you run inwords heart FFT, then you get a description of the actual tree. So this tree is if TAL is either RD or FD, and in this case, TAL is a measure of how well blood flows to the heart. And the possible values of this can be N for normal, FD for fixed defect, or RD for reversible defect. So the tree is going to say, if blood is not flowing well to the heart, then immediately predict that they're at high risk. If that's not the case, then move on to the second Q. If CP, which is the type of chest pain, is not equal to A, where A is asymptomatic, then immediately predict low risk. And then finally, there's the last Q, which is CA, which is the number of major vessels colored by fluoroscopy. I'm not even sure what that is. So now you want to actually see the tree? Well, just plot the object. So here we see the exact same tree I just described to you. We have the titles and the decision labels all passed through because I've already defined those when I created the object. You can also specify which, actually that come up next. So you'll notice up here I've said stats equals false. And that's me telling it I don't want to see an additional summary statistics, I just want to see the tree. But if I don't include that argument, just by default, then I get a lot more information. So here what I get is 3 separate panels. On the top panel, I have a description of the data set. So here I'm told there's 153 cases. I can see how many were high risk. In this case, there were 73. How many were low risk? In this case, there were 80. I also got levels telling me what overall percentage that was. Now in the middle panel, this is really where all the action is. Here I see the same tree again, but now I get to see actually how this tree is making decisions for this data set, separated by the different types of decisions. So on the right side here, these are all the decisions for high risk. And one of 2 things can happen when the tree decides high risk. You can either have a false alarm, so these are errors of people that actually were low risk, that did not have heart disease, that the tree is incorrectly classified as having heart disease. And here you can see there were 18 mistakes. Now next to that, you can also see that there were 54 cases that were hits. So these are true high-risk patients that were correctly classified. And moving on down the tree, we can see exactly how it's making decisions. And what I think is really nice about this is it's showing the information to the user in terms of icon arrays, which psychology research has shown is a much more transparent way of presenting probabilistic information than just probabilities. So people have a hard time just naturally understanding what probabilities are. But if you show them an icon array, things become much clearer and much more intuitive. Now in the bottom of the panel here, I have some summary statistics. So here's a 2x2 classification table indicating just summaries of all of these correct rejections, misses, false alarms, and hits across the entire tree. I get some levels as well. So some of these measures here are specific to the tree. One, for example, is this MCU. And this is what we call mean Qs used. Or in other words, on average, how much information does this tree need to make a decision? And in this case, it's 1.7. So all these patients were classified after 1 piece, these after 2, and the bottom one, these were all classified after 3. But on average, the tree needed 1.7 pieces of information to make a decision. PCI here is percent of Qs ignored. And this is a way of representing, out of the entire data set, how much did the tree ignore when making its decisions? So in this case, I see that this tree when being applied to this data set, ignored 88% of the data. And I also have additional classic summary statistics of the performance. Now, on the bottom right here, I have an ROC curve, and let me zoom in on that. So here, I can see the performance of the specific tree that I'm plotting, which is highlighted in green. So this is tree number 1. And I also see several other points here. So these other trees, which are labeled 1 to 7, these are other trees that also have been created in the object. In addition to that, we can see the performance by default of other competitive algorithms. So by default, the package will also run CART on the data, which is just standard decision trees that are not necessarily fast and frugal. Logistic regression, random forest, support vector machines. You can turn these off if you don't want them, but by default, they come in. So somebody looking at this might say, okay, well, that tree was nice, but what does this tree look like? Or what if I wanted to really maximize my sensitivity? So you can see tree here, tree number 6, has a really, really high sensitivity. Well, if you want to look at that tree, just indicate what tree as a numeric when plotting the object. So now I'm going to say plot heart FFT, and now I want tree number 6. And here's the tree. And what you can see quite quickly is, well, now we see why this tree has such a high sensitivity, because all of the exits for all of the nodes except for the last one are positive exits. So this tree really, really wants to classify people as having heart disease. And the only way that it's going to classify you as not having heart disease if you can make it all the way to the bottom. And that's why this has such a high sensitivity. But I could also go on the opposite end. Maybe I say, no, I want a tree that has a really high specificity. Well, if we looked at the ROC curve, that's tree number 7, and here's how that one looks. So here we can see this tree really wants to classify people as saying, no, you don't have heart disease. And only if you get to the very end will then decide, yes, you have heart disease. So I think what's nice about this package is that it makes a very transparent, simple model. But I think it's also important that this algorithm can provide good predictions. So here's one prediction simulation I did, taking 10 data sets from the UCI machine learning database. I just did 50% training, 50% testing, and I compared FFTrees to regular decision trees with rpart, regression, random forest, and a few others. And for this simulation, I'm just going to show you for the criterion balanced accuracy. So this is just the average of sensitivity and specificity. Before I get you to the performance statistics, let me show you how quickly these trees made decisions. So here on the x-axis, I have, again, this mean queues used to make a decision. So on average, how much information did these trees need to make a decision? On the y-axis here, I have this percent of information ignored. And here are the results for all of the data sets. And you can see here that and these data sets have a huge variety in their number of cases, their number of queues. But because these trees are so restricted, the one data set that had the highest number of mean queues used was still under 3, so 2.5 on average. And these trees are ignoring around at least 70% of the data that they're given. So they're making decisions really, really quickly based on very, very limited information. So how well did they actually perform on this balanced accuracy? Here's the training balanced accuracy distributions. So here on the far left here, I have the fast and frugal trees. And then I have CART, naive Bayes, logistic regression, regularized logistic regression, random forest, and support vector machines. And this is just for the training data. And here we see that the trees, on average, are getting around 85% in their mean balanced accuracy. So it's kind of in the middle of the pack. But we see, for example, that random forests here are by far dominating all other algorithms in training. But of course, we don't care about training. We want to know about prediction. And here's the similar results for prediction. And here we find that now the FFTrees have not suffered so much from overfitting, and now they're right in line with regularized regression, random forest, and support vector machines is a bit higher in this case. Now again, I know a lot of you are thinking, okay, but that's just one performance criterion. What about other ones? And I totally agree, that would also need to be done. For this simulation, I was just focused on balanced accuracy. So my point here is not to say that, yes, this represents how well the trees do in all possible data sets relative to other algorithms. But for some accuracy statistics, it seems to be that they're working quite well. And here's the distribution for all different data sets. You might say, okay, well, that was averaged over all the data sets. What about the individual ones? And here's the results for each data set. And no matter which data set you look at, the trees are right up there, quite competitive with the other algorithms. And next to each of the trees, I have examples of or next to each of the data sets, examples of trees created for each of them. So some of these, for example, this breast cancer data set, this only had 2 nodes, versus this dermatology data set, this required 4 nodes when trained on the entire data set. Let me give you a few other examples of some of the data sets. So this was one on mushrooms. So this is trying to classify mushrooms as being poisonous or not. And this tree is able to make decisions based on 2 cues, the first one being odor. So how does the mushroom smell? Based solely on that cue, it's classifying all of these cases. The next cue is spore PC. To be quite honest, I'm not exactly sure what that is. But it's making quite good classifications based on just 2 cues. Here's a breast cancer data set. Again, making pretty good decisions just based on 2 pieces of information. Here's a classic Titanic data set predicting which passengers of that Titanic would survive. And we see that the first cue the tree has found is sex. So if you're female, then it's going to predict you survived. Next, moving on to your class and then your age. Yeah. Now, there's many other additional features in the package that, unfortunately, I don't have time for. There's really good guides in the package. So if you open up the main package guide, you'll see a list of several different vignettes taking you through all the different visualizations, ways to customize the tree growing algorithm. I'll just take you through a couple of them right now. So one thing I wanted to do when creating this package is I want the user to be very active in creating these trees. So if a user says, OK, that's a nice tree, but what would happen if I exchanged the order of these cues? Or what if I used a different decision criterion? How would that affect things? So I want to make it really easy for people to do that. So to create your own tree manually, all you have to do is just type it in as text. So for example, if I now create trees on the training data set, all I have to say is my tree is, and then just type it. If cholesterol is greater than 350, predict true. Otherwise, if CP is not equal to A, predict false. Or if age is less than or equal to 35, predict false. Otherwise, predict true. And then the algorithm will then, or the function will then bypass the tree construction algorithm, parse this text, and create this specific tree that you specified, and then apply it to the data. Another thing you can do in the package is include queue costs. Now, for some data sets, this might not be relevant because you have access to tons of data. But for some decision problems, for example, in medical diagnosis, specific queues can come at real costs. So you might want to take that into account when developing the algorithm. So for example, in the heart disease data set, here's 6 of the possible queues. And the most expensive queues are tall, CA, and slope, which each of these cost around $100 to get these tests. And if I create the tree without incorporating the costs, the tree gives me I get this result. The average cost of running this tree would be $120 across all patients with an accuracy of about 80%. But if I now rerun the algorithm, but now in this case, I tell it, here's the cost of the queues, which I include as a data frame called heart.cost. I can also include the cost of different decision outcomes here. Then I get this tree. Now this tree is now only using these queues, CP and Trust BPS. These queues are almost free. This tree now has a cost of $1.56 with an accuracy of 75%. So with a decrease of only 5% in accuracy, I have a tree that is about 100-fold cheaper. So a question that people frequently ask me when I tell them about the package is, well, when should I use an FFT? Well, like any important decision, there should be a fast and frugal tree for that, which there is. So I'll present it to you now. The first question I would ask is about implementation. So is this an algorithm that's going to be implemented by a person without a computational aid? If that's the case, I would consider an FFT. This is really tailor-made for that. And the second question I would ask is costs. Are there actual temporal or monetary costs to gathering data? If so, then I would consider an FFT. Third, transparency. Is it important for people to quickly understand how the algorithm works? If that is the case, then I would consider an FFT. And I think this is really important because the transparency of the trees not only show when it's doing well, it also shows when it's not doing well at all, when it's doing poorly. So for example, if you have a heart disease fast and frugal tree, and you develop it in 1 year, but the next year, all of a sudden, it starts failing. It's making tons of bad decisions. Well, it's really easy to see in the tree where it's making the bad decisions and make a correction. And the final question I would ask after this is prediction. Do FFTs make predictions as well as other algorithms in the problem domain? If yes, then I would stick with the simpler FFT. If not, then I would use another algorithm. I would not consider FFTs for this task. So that about wraps it up. This package is described in a publication in press at Judgment and Decision Making. I'd like to thank my collaborators, Wolfgang Geismeier, Hans-Jörg Nett, and Jan Wojka. And here's links to the GitHub repository, this presentation, and instructions for installing the package and opening the guide. Thank you.
So thank you for your talk and you for your patience, because we are a little bit over the time, 2 minutes from the beginning, and now it's accumulated a little bit. So we have, in theory, no questions, but if someone is in front and has a very urgent questions, should be possible. Because I think there's indeed lots of discussion, especially about last aspects about financial consequences. So please contact the speaker in the lunch break. So thank you for attending. See you in the next